2, 1. Alright. Okay, so let's wrap up Chapter 7, talking about the Laplace transform, by doing a couple of examples of solving second-order initial value problems using the Laplace transform. Okay. So as a sort of general setup here, for any second-order linear constant coefficient initial value problem, looking like this, anything of this form can be solved using the Laplace transform. And in fact, you could just do it. Boom, here you go, I did it. A lot of work, but let's break it up. So you can take the Laplace transform of the left-hand side, take the Laplace transform of the right. Now, right, this is our mystery function, our non-homogeneity, whatever that may be. Now, the left-hand side will always go the exact same way no matter what. It will always break down like this, and I want to point something out here. The Laplace transform of y will always be multiplying something that looks like this. Hey, that's the auxiliary equation now, isn't it? Yes, it is. So when you do your work, this is a great little test. If you do out the work and you see you've got something times the Laplace transform, and it's not the auxiliary equation for the associated homogeneous, something went wrong. Alright, so then we can add this stuff over here, and depending on what A, B, and C are, you can predict what these are going to be. So it's worth noting that whatever these are will cause whatever behavior to occur, right? Whether we'll get sines or cosines or whatever needs to occur there. But anyway, so this is just the general form to give you an idea of how it's going to work. You don't need to have this memorized or have this at the ready, but it's this is worthwhile to work out the details and kind of see where this is always going to land. It'll always land at stuff that looks like this. Now, depending on the roots of the auxiliary equation, these terms over here are going to have wildly different behavior. And of course, depending on the behavior of the non-homogeneity, this term right here is, depending on what's going on there, that one's going to be fun. Alright, so that being said, let's give it a spin. Let's solve a second-order constant coefficient initial value problem. Alright, so take the Laplace transform. Okay, so we'll take the Laplace transform both sides. Laplace transform e to the t is 1 over s minus 1, right? The 10, Laplace transform is linear, goes along for the ride. So that part on the right-hand side is just going to stay there. Now let's look at the left-hand side. Alright, so I'm going to take the Laplace transform of the second derivative. That means we lose a derivative, multiply by s, and then subtract off y prime of 0. Okay, and then you do it again. Peel off a derivative, multiply by s, subtract off by the function evaluated at 0. Alright, y prime of 0 is 0, so that's gone. Y of 0 is 1, so that term gets added over here, specifically an s gets added over. Here I see I've got s squared plus 4, and then I go back here and I check. That is the auxiliary equation, so I did that right. Divide over the s squared plus 4, and boom, there we go. We have two functions we need to inverse Laplace. One of whom is super easy. I immediately see that this term right here, that's going to give me cosine of 2t. Now, the one that's going to be a little bit more fun is dealing with this term right here. Okay. Alright, so like I said, we've got some inverse Laplaces to do. So let's take care of this one first, because this is the more challenging one, right? We've already pointed out that the other one is just for free. It's just immediately we see what it is. You got to do the partial fractions. So again, my recommendation, when you do the cross multiplication, multiply all the terms out, and then match coefficients. Again, you can plug in s values to delete terms if you want, like plug in s equals 1, plug in s equals 0. And if you're daring, if you were a real rock and roller, you would plug in 2i, because that would delete this term. And right, if you really wanted to impress somebody, you would actually factor this, right, instead of leaving it as an irreduced quadratic like this, right? So it's worth noting that with complex numbers flying around, partial fractions can get a little bit more interesting if you wanted to make them a little bit more spicy. But you don't need to do that. But if you want a good challenge, try to use complex numbers to solve your partial fractions. Okay. But anyway, match the coefficients. not too difficult to solve here and get that A is 2, B is minus 2, and C is minus 2. Alright, so equipped with those numbers, the inverse Laplace of this is now easily seen. So, it's this. The inverse Laplace is linear, and note how I split it up. I split up the 2 terms, so the 1 over s minus 1. I'm going to pick up an e to the t there. Here, I pulled this apart, so I had s over s squared plus 4. I know that's going to give me cosine. And here, I made sure I had a 2, because I've got the 4 down here, so the 2 needs to match that, right? 4 is 2 squared. So I pick up the sine term, and boom, there we go. The first term has been inverse Laplaced. Now, equipped with that information, we can produce the solution. As we already noted, this term was for free. It was just the cosine. The inverse Laplace of this is that whole piece right there. You add them up, and that's it. I've solved this second order initial value problem via the Laplace transform. Right, so note, if you were to do this the other way, we would need to solve for the roots of the auxiliary equation, then use either undetermined coefficients or variation parameters. This is ripe for undetermined coefficients. Figure out that 2e to the t is the thing we want. That's not surprising. You can plug that in and immediately see that works. And then you'd have to plug in your initial conditions here to solve for the C1 and the C2. That would show up here. Here, the C1 and the C2 would be both equal to -1. All right. Not too bad. So, hey, there you go. Pretty typical second-order initial value problem solved using inverse Laplace transforms. Pretty cool. All right. Well, let's get a really let's wrap things up with the Laplace transform of a real fun initial value problem. All right. So let's say you've got a mass spring system, no dampening, so free motion. And it's sitting at rest in the equilibrium position. So it's not moving, it's just hanging out. Alright, so let's get it happen. So Albert Einstein's trying to get work done. But that Martian, Von Neumann, he's just blasting music on his gramophone. And after a minute of that nonsense, Einstein's had enough. And he takes out his patented Einstein hammer. The Hebrew hammer, yes, boom. Oh, there you go. There's a reference nobody's going to get. And he hits that mass spring system with a solid impulse of 2 Newton seconds to let off some steam. All right. There you go. All right. So, this fun story brought to you by apparently something that actually did happen. Einstein and Von Neumann. Einstein, obviously, you've heard of him. You may have heard of John Von Neumann. Von Neumann is... There's a lot of, who was the best mathematician ever, who was, one of the most talented math people ever. And usually when that debate happens, Euler and Gauss are usually the ones that come to the forefront for a variety of reasons. But Von Neumann really is... He's either third place or he is first place. His computational skills are legendary. He was essentially a human computer in terms of computing. And beyond that, when it came to theoretical work, he was... the stuff that's named after him is just... Woof. He is a wildly talented mathematician. Also, he was apparently an insufferable kind of character. So his office was next to Einstein's, and Von Neumann lived in chaos, apparently. He would read books while he drove, apparently, and a bunch of other stuff. So he would constantly blast music, and apparently it would piss Einstein off. And this brought to you by an actual thing that may have happened. But anyway, so as an initial value problem, what is this going to look like? So this impulse, this instantaneous hitting a mass spring system, right? It's not like the other one we were talking about where you had a constant amount of pressure, where you had this, where here now you hit it with a hammer, so bang, crack it, and, you hit it and you whip back. You don't hit it and hold on to it. So there's this instantaneous impulse. And it turns out that the Dirac delta models that perfectly, right? Because again, remember the Dirac delta is 0 everywhere, except for when it turns on, where it blows off to infinity. Okay, now again, it's not a real function, that's not what it's really like. But, right, because you can talk about the amount of impulse that it does by putting a scalar here. So this is not like a true initial value problem. In some sense, it's like a symbolic initial value problem, if that makes sense. Right, because this is, again, here on the right-hand side, is not a function, it's a distribution. So there's a way of making all of this work out very nicely. But we can treat it like we normally do, so let's hit this thing with a Laplace transform. Okay, so we're going to solve this problem. We're going to find out Einstein's mass spring system. How is the behavior of it going to be? After he smacks it with a hammer. Okay, so hit it with the Laplace transform. So we're at equilibrium and there's no motion, so that none of those terms show up. Hey, the auxiliary equation, s squared plus 1, there it is. The Laplace transform of the Dirac delta, remember, is e to the s. So here for the shift, did Dirac delta, the normal Dirac delta, has a Laplace transform of 1. Okay, and so we bring this over here, and then now we see this, we see a 2, and then we notice, hey, 1 over s squared plus 1, I know that's sine of t, but it's being multiplied by an e to the negative s, so when I inverse Laplace it, the Heaviside function shows up, so I get this translation to the t-axis. So note specifically, right, if we were to think about what this function does, it does nothing until t equals 1, where a unit impulse of 2 activates and it turns on. Right, and then, since it's a mass spring system and no dampening, right, it will then experience normal sine oscillations. It's just delayed until t equals 1. Nice. That's really cool that we can now very clearly and explicitly mathematically model that sort of system, and we get a solution that is legitimately what you would expect it to be. Alright, boom. Cool stuff. So there we go, a couple of examples of initial value problems and solving them using the Laplace transform to play us off. Alright, and with that we are done with second order linear differential equations. But we're not done with differential equations just yet. I wonder what we're going to do next. You'll just have to find out.